Hello, tonight's assignment is on two topics that you may have seen before in different classes, density and percent error. Density you might have covered if you took conceptual physics here. Percent error may have been covered in one of your math classes, depending on how much math you've had. This should go pretty quickly. They're both relatively simple concepts. We'll start with density. Density is essentially a measurement of how much matter, how many atoms are crammed into a specific volume of space. There is an equation for density, D equals m over v, where D is for density. We'll get into what the units of density are in a moment. M is for mass, the amount of matter or number of atoms crammed into a particular volume, and the V is for volume. In this class, when we deal with density, in mass, we are always going to be measuring in grams. When you do experiments with mass in this class, you will find that our electronic digital scales have a capacity to measure to the nearest tenth or the nearest hundredth. So let's say you measure something on one of the more accurate and precise scales that we have, you might find that it has a mass of 21.58 grams. The mass that you get off of the scale will be one of the factors that controls how many significant figures you can use in your answers for these types of problems. Volume is measured in multiple different ways, but in this class we will use two. The volume of any object that we need the density for will be in cubic centimeters or in milliliters. There's a nice relationship between these two. A cubic centimeter, that is the volume contained in a cube that's 1 by 1 by 1 centimeter, is equal to the volume of a milliliter. So if this is a graduated cylinder and each one of these black marks is 1 milliliter is the same volume as 1 cubic centimeter. So we can almost use these units interchangeably. This means that your units for density are going to be either grams per centimeter cubed or grams per milliliter, depending on which unit your measurements are made in. There are a couple of other handy things that are useful to know when you're doing problems with these. One is that water, the chemical formula H2O, meaning you have 2 hydrogens and 1 oxygen, has a density of 1 gram per milliliter, exactly. And so we could actually extend that out and say it's 1.00 grams per milliliter, so that you would have at least 3 sig figs in an answer if you were to do a calculation like that. Now, in some cases in this class, you'll have to calculate density when I'm giving you mass and volume, but in other cases, I won't give you mass and volume. I'll give you 2 out of the 3 variables here, and you'll have to calculate the third. Let me give you an example. Gold, the chemical symbol of gold is Au, and the density of gold is 19.32 grams per cubic centimeter. Let's say you have a gold bar, and the mass of the gold bar is 107.3 grams, which is a fairly substantially sized gold bar, worth quite a bit of money. And the question is, what's our volume? Well, you can plug these into the formula and solve, or you can rearrange the formula first, which is what I prefer to do. If we start D equals m over v, we want to get v by itself or volume by itself because that's what we're solving for. So we multiply both sides by volume, we divide both sides by density, and we get volume equals mass over density. Then we plug in our numbers. The mass is 107.3 grams. The density is 19.32 grams per centimeter cubed. If you flipped over these fractions, you would find that the grams cancel out, and so your answer is going to be in centimeters cubed. And if you do the calculation, you'll find that you have an answer something like this, 5.5538 centimeters cubed. But we're not quite done because we have to get the answer in the correct number of sig figs. So we look at our problem here. We are given 4 sig figs here and 4 here, which means that our answer should have 4 sig figs. So we have to round this to 5.554 centimeters cubed. And that's the volume of our gold bar. It would actually be a relatively small gold bar, but again, worth quite a bit of money. That should give you all the information you need in order to solve all of the problems regarding density for your homework. Those problems are, I don't have it at hand, I believe on one of the sheets that you have on the back page of your homework packet. The second thing that you have to know in order to be able to solve those problems is what percent error is. So we'll go over that next. The reason that we're calculating percent error right now is that we're doing a lab on density in which you will be finding the density of various objects or various known materials, like the density of copper, for example, and comparing the density that you experimentally measure in lab to the accepted value that scientists everywhere agree upon. And you'll have to figure out how far off your experimental measurements were from the accepted value. And to do that, we use a calculation we call percent error. There are a variety of different statistical measures that you can use to tell how far off experimental values are from accepted values. We're just choosing this specific one. To calculate percent error, there are a couple of things that you need to be able to do. The first is to find the error. The error is just how far your value is from the accepted value. So the error in your measurement is equal to the absolute value of the accepted value minus the experimental value. So in this case, let's say that you are measuring the density of copper, and your measurements allow you to calculate that the density of copper is equal to 9.04 grams per cubic centimeter. However, the accepted value for the density of copper is a little bit less than that. It's 8.96 grams per centimeter cubed. And we want a measurement of how far off. So the first thing we do is calculate error. In this case, the error is equal to the absolute value of the accepted value minus the experimental value. Because of the absolute value signs, the error is always going to be a positive number. This means that your error is equivalent to 0.08. And for the lab that we do, that's a relatively small percent error. The second thing that you have to measure or calculate is percent error, which is just a calculation based on your calculation of error. So percent error equals your calculated error divided by the accepted value times 100. And so your percent error in this particular case is going to equal 0.08 divided by the accepted value again, 8.96 times 100. And when you do this, you'll find that you only have an error of about 0.8%. If you get an error that small in lab, you're doing quite well. That should be enough information for you to do all the problems on the back page of your homework packet. You'll have to let me know if you have any trouble tomorrow in class. Enjoy.